Hello everyone, I'm Krishna Regmi and today I'm going to present our ICCB 2019 work. The work is about bridging the domain gap for ground to aerial image matching. So the work is about cross-view image matching, where we have the images from ground view, the ground query image, and a database of aerial images. There are multiple aerial images, and the problem is to find the match between the images in these two views. So it is a very challenging problem because of the drastic difference in the viewpoints between these images. So we propose a method to first generate the image in the target view and then use it for together with the query image to do the image matching and find the match. So we employ the joint feature learning and feature fusion process, and we also use multi-scale feature aggregation approach that I'll be talking in details. The previous works in cross-view image matching use Siamese type architectures where you have two branches of networks that take the aerial and the ground images and learn the features. Also, the previous work in CVPR 18 use net-blood features to learn better features from these two set of images and do the feature matching. While in our approach, we first try to generate the image in the target view that looks very similar to the reference database images and then use them together for the cross-view image matching. So let's walk through our approach in brief. So first, this is a ground level panorama, which is our query image, and we use the image along with the edge map to generate the image in the target view, which is the aerial image, and also the semantic segmentation map using a GAN-based approach. Then we use the synthesized aerial image IA prime along with the ground image IG and the aerial image IA and pass through the encoder networks that learn the features for these images, and then from the first two features FG and FA prime that belong to the images IG and IA prime, we combine them together to find a query feature FG star. Also from the lower branch, we get the feature FA star that we use to do the feature matching between the query and the target images. So let's look at our generator architecture. So the generator architecture is an encoder-decoder type architecture which is inspired from XFork network from our previous CVPR paper. So the network has encoder. The encoder is shown here, which has following layers, and it learns the representation for the input images. And in the bottleneck, we have the features here that goes through two branches. Because this is a fork type architecture, we have the upper branch that learns that has a decoder that learns to generate the aerial image, and the lower branch learns to synthesize the aerial segmentation map. Also, we share the weights for the first 6 layers of the decoder branch because both of them are learning to find the representation for the aerial domain images. So now we show the encoder architecture that is used in our joint feature learning network. So the triangle shown as the triangles that represent the encoder architecture have the following layers. So we have 5 conv plus ReLU layers and 3 conv plus ReLU followed by dropout layers. So we get the features from the final layer as well as the features from the previous 2 layers, and then we combine them together to find the multi-scale features for the given input, and we pass it through the fully connected layer for feature dimension reduction and find the final representation for the input image. For our joint feature learning approach, so traditionally we have image IG, which is the aerial ground image, and we have image IA, that is the aerial image that go through the encoder networks to learn the features FG and FA by minimizing the distance between them. In our approach, we also have the pre-trained generator network that learns to generate image IA prime. And then we use this image, pass through the encoder network to learn the features FF prime for the synthesized image. And then, so here the 2 networks share the weights because both of them are looking at the images from the aerial view. So we train this network together with the auxiliary loss and the original loss, And the objective of using the auxiliary loss here is because we are only using feature FA prime to bring the feature FA closer to FG, and ultimately our objective is to bridge the gap between FG and FA. So this is used only during the training, and so we use features FG and FA during the testing. So the next approach is feature fusion, where we take the architecture from joint feature learning that gives us features FG, FA prime, and FA for images IG and IA. And then, since feature FA prime was very useful in our joint feature learning approach, we didn't use it during the testing. So here we propose to combine that with the feature FG and then find a common representation for the ground image, so, which is FG star. Similarly, for the feature FA was optimized with respect to FA prime and FG, so we pass it through a fully connected layer to learn feature FA prime, and then we train this network to obtain the final features FG star and FA star for the input images IG and IA. So we use the following loss functions in our network. Basically, we start with the triplet loss, which is as shown here, where we have dp and dn are the distances from the anchor to the positive and negative features, and m is the margin, which can be shown as here max of 0, m plus d. The problem with triplet loss is we have to decide the value of m, what should be the value of margin. So there is a better way to do that, is use the soft margin triplet loss, where we do not need to define m, and then there is another improved version of weighted soft margin triplet loss, where alpha is the weight. And we use this weighted soft margin triplet loss in our experiments. Also, for our joint feature learning experiments, we had two loss terms, the main loss and the auxiliary loss. So the main loss was between the ground images and the aerial images, and the auxiliary loss was between the aerial image and the synthesized aerial for ground image, and we used lambda 1 and lambda 2 to weigh the loss terms. So for our experiments, we used aerial and ground image as the cross-view image pairs. And so we used two datasets. The first one is CVUSA dataset that has 35K training samples and 8,884 pairs of test samples, and it covers the rural areas of US. The other dataset was a newly collected dataset by us. It covers urban areas of Orlando and Pittsburgh, and it has GPS information available. So the training set has 1,910 images, and the test set has 722 image pairs. So let's look at some of the results. So on CVUSA dataset, let's look at this quantitative evaluation. We have this evaluation on top 1, top 10, and top 1% accuracies. So first we show the result on two-stream baseline, where we use aerial image and synthesized aerial from ground, and these are the numbers. Then we also have the two-stream baseline, where we use ground image as it is with the aerial images, and these are the numbers, which are a little better than the first results. For joint feature learning, we have two results, where we use either the synthesized aerial or the ground image with the original aerial images, and these are the numbers. And finally, we have our feature fusion method, which does the best. Here are some of the results from the previous state-of-the-art methods, and we can see that the proposed feature fusion method does consistently better than the previous methods for top 1, top 10, and top 1% accuracies. So let's look at the vertical accuracies. So here on the x-axis, we show the top k, and on the y-axis, we show the vertical at top k. So this is the result for CBM-Net1, CVPR18 org, and here is the CBM-Net2. This one is a little better, less than the CBM-Net1. So here are results from our methods, two-stream baseline with aerial image and the synthesized aerial for ground. So this one is for our ground and aerial images. So we have joint feature learning method shown in the green. And finally, we have the feature fusion result on the red curve. So we conducted some ablation studies. So we used, one of the ablation studies was using the single scale features where we only consider the features from the final layer, and these are the numbers. So the other ablation study was using global average pooling to reduce the feature dimensions. And also the next ablation was using weight sharing as done by previous methods. And these are the results that we obtained when we used our design choice of using multi-scale features, no global average pooling, and no weight sharing. Let's look at some of the image retrieval results. First, we show the ground query image, followed by the synthesized aerial image that we get from the generator. And then we show the top 5 matches. The result on the green box is the correct match, which is the ground truth. So here are more examples. And here are a couple of more examples where the correct match was obtained at the 2nd and 4th position, respectively. Let's look at some of the failure cases. So this is a ground query image, and this is a synthesized aerial image for it. So we show the top 1 match, the correct match, which is the ground truth image, and the position of the correct match. So here it means that the correct match was retrieved at 13th position. And I think the problem here is because if we look at the correct match, there is some water on the right lower side of the image, which cannot be inferred from the ground query image nor from the synthesized aerial image. So here is another failure case where the top 1 and the ground truth images are very similar to each other, and this is a problem where a lot of images in the gallery set or the database are very similar to each other, so it's very complex. So here is another failure case where the synthesized image is not able to generate the houses, and because of the occlusion on the query image, so it is very problematic for the network to find the correct match. So here is one more example of failure case where the network is not able to learn the size of the house that is seen in the query image, so it cannot find the correct match, which should have a very large building in the top view. Now let's look at the results for the OP dataset. So first, the retrieval performances. So these are the numbers for top 1 accuracies using two-stream network, joint feature learning, and feature fusion approaches. And here we show the error threshold versus recall accuracy. So here error at threshold x means that if the retrieved image is within a distance of meter x, then the retrieval is correct, otherwise it is wrong. Let's look at some more qualitative results. So here we show the ground query image followed by top 5 matches, the green one being the correct match. And the numbers below each of these images show the distances of these images from the ground query. So the correct match, which was at a distance of 0.0 meter, was the closest match. So here are more examples of the qualitative results with their distances and some more. Let's look at the features obtained by our network are very useful for our experiments. So here we show the features for aerial images using our two-stream network, which is a baseline network. And here each plot represents an aerial image, and these are the TSNE representation of the feature maps, which is the 2D projection of the features. So we also show the features for the ground image, and we see that they do not align that well. On the right-hand side, we show the features that we obtain for the feature fusion method, and these are the features for aerial images. And we show the features for the ground images, and we can see they overlap more. And this is why our network is doing better, and we are getting better results. We also studied the problem in the reverse directions, meaning we tried to use the ground. We did the aerial to ground matching, where aerial image is the query, and we first synthesized the ground image from the aerial query and tried to use our method to do the aerial to ground retrieval. So here are some of the results. So using the two-stream baseline with ground image and the synthesized ground from aerial, we get these numbers. So when we use the two-stream network with aerial image as it is, with the ground images, these are the numbers. So when we use joint feature learning, we have two combinations that give us these numbers. And finally, when we use the feature fusion, we get a number which are very consistent with the ground to aerial matching. So all of these numbers follow the similar pattern of the other directions. Let's look at some image retrieval examples. So given the aerial query image here, we first synthesize the ground panorama as shown, and then we find the top 5 matches that we have shown here, the green one being the correct match. We have more examples and more examples. So over here as well, we can see the synthesized ground images are very similar to the target images or the ground truth images in the ground view. We show the recall accuracies here. On the x-axis, we have the top K, and on y-axis, we have the recall at top K. And first, we show the two-stream network results for ground image and the synthesized ground from aerial. Then we have the plot for original aerial image and original ground images. And next, we have the results for joint feature learning using the synthesized image and the original aerial image. And finally, we have the result for the feature fusion. So in conclusion, we proposed a novel and practical approach to cross-view matching problem by first synthesizing the image in the target view so that it could be utilized to bridge the domain gap between these two contrasting views. And we are able to obtain significant improvement in top 1 and top 10 accuracies on state-of-the-art methods on CVUSA dataset. Thank you.